Please click on subscribe button and click on bell icon for more interesting updates on civil engineering concepts.
Hello everyone, welcome back to my YouTube channel Civil Engineering by Shravan. And if you are not yet subscribed to my channel, please click on subscribe button and click on bell icon for more interesting updates on civil engineering topics. So in this class, I will explain you complete designing of the simply supported slab according to IS456-2000 code provision standard system. So in the previous class, we are done with cantilever slab design and complete twin tower building design by using manual method as well as the StatPro software. So you can watch those videos. I will provide you the video links in above card link and below description of this video. So now we can see this is the typical floor plan. I am considering center to center distance between the columns for this particular system. So it is consisting of the cantilever slab at this corner. Again, it will be consisting of the simply supported slab section at this level. Okay, so now we can see this is the section just I am considering here, which is consisting of approximately 2.5 meter. I am taking not 3 meter here. So 2.5 meter S3 section, which is nothing but the slab 3 section I am designing for this structural model. So I will upload this PDF in the Civil Engineering Shravan application. You can download the PDF and you can check the complete details about the complete step-by-step calculation part, which is related to the cantilever slab section design according to IS456-2000 code provision standard system. So these are the steps to be followed for designing of the simply supported slab section. So initially we need to calculate the depth of the slab, and second one is we need to calculate the loads, and third one is we have to calculate the moment of resistance as well as the bending moment for this slab section. Again, fourth step is to calculate the main steel calculation, and we have to check for the deflection for the main steel section. And sixth step is related to distribution steel calculation, and seventh step is related to check for the shear, and eighth step, last step, which is nothing but the development length calculation. So here for this building structural model, I am taking grade of the concrete is M20 grade concrete provision standard system. In the same process, grade of the steel is 415 grade steel provision standard system. So these are the specification we are considering for this model. So we will start with the complete designing of the slab section, which is a simply supported slab by using IS456-2000 code. Please click on subscribe button and click on bell icon for more interesting updates on civil engineering topics, and share this video with your friends for getting more knowledge regarding this complete designing. And you can click on the like button so that it will help me for creating the better content for you. So here I am selecting my first step, which is related to depth calculation of the slab. So now we can see this is the first step, which is related to the depth calculation of the slab, which is similar to that of the cantilever slab. So initially we need to consider the depth calculation formula is D equals to span divided by multiplication factor into RB value. Basically RB is the length of the slab and width of the slab ratio. So here we are considering the span is approximately 2.5 meter according to our consideration, 2.5 meter, which is of 2500 mm. So for simply supported slab section, the value of the RB, which is of L by B ratio, is 20 mm. So you can consider here 20, here the factor is 20 here. So again, if you consider the L by is 20, then let us assume the value of the PT. Initially we need to assume the PT value. So in the previous class, which is related to the cantilever slab, we are assuming 0.2% as PT value. So in this class, I am taking example of 0.3% for the M20 grade concrete and HYSD bar of 415, which is related to simply supported slab section. So now we have to calculate the value of FS value in order to get this multiplication factor. Basically we have the multiplication factor for the curve, which is related to the percentage of the steel and FS value. So FS is related to 0.58 times of FI value. We have to consider this formula. So 0.58 multiplied by 415 is the grade of the steel. So if I substitute this value, then it will comes under 240 Newton per mm square is the value of the FS we had to consider for this model, building structural model. Now we have to consider these two factors, which is related to FS of 240 and PT 0.3. So for the respected value of FS of 240, this is the curve which is related to the 240. Again, it is consisting of the PT 0.3. So now we can see this is the 0.3 PT value. For this PT of 0.3 and for the FS of 240, the value of the multiplication factor is 1.48 here. We have to consider. So after considering the 1.48 multiplication factor, we have to calculate the depth, which is having the formula is span divided by multiplication factor into RB value. 2500 divided by 1.48 into 20, which is comes under 84.46 mm. So let us consider, assume depth of the slab is approximately, just I am taking rough as 90 mm value. So by taking the cover as 20 mm for the slab section, so we have to consider the total depth is d plus d, which is of 90 plus 20, which is approximately equal to 110 mm for this slab section. So this is the first step for calculating the depth of the slab. So for calculating the depth of the slab, we have to use the formula depth d equals to span divided by multiplication factor into RB value. So RB value is directly available in the class 23.2.1 from the IS codebook provision standard system, and multiplication factor is taken from this figure number 4 of multiplication factor for tension reinforcement section, which is available in the IS codebook. Okay, this is the formula generally we will use for calculating the FS value. So now after calculating the depth of the slab, now we have to calculate the loads. So let us consider, these are the calculation part which is related to the loads by considering the width of the slab is approximately 100 mm panel. So you can see here, this is the width of the slab, just I am taking here as 3 meter, and this is the length of the slab 2.5 meter, here I am considering. For the 3 meter width, I will divide this 3 meter width into 3 panels, each will be consisting of 1 meter section. So initially I will calculate the reinforcement for this 1 meter width of the slab. Then I will distribute that respective reinforcement to the remaining sections. Okay. So now we can see, firstly we have to calculate the self weight of the slab. So self weight is having the formula is unit weight of the RCC slab into area of the slab. So unit weight is RCC is 25. So if I multiply this value with the thickness of the slab, which is of 0.11 into length of the width of the slab, which is of 1 meter, then it will comes under 2.75 kilonewton per meter is the value of the self weight of the slab. So now second step is to calculate the floor finishing load. So generally we will consider value of the floor finishing load is 2 kilonewton per meter square. So here I am assuming the value is 1.75 kilonewton per meter intensity. Now again we will assume the live load value. Just I am considering this live load is consisting of 1.5 kilonewton per meter for the simply supported slab section. So now after this we have to calculate the total load for this particular slab section, which is the summation of the self weight and floor finishing load and live load, which is comes under the value is 6 kilonewton per meter intensity value. So after this we have to calculate the ultimate load, which is related to the design load. So we have to multiply this respected value of 6 kilonewton per meter with 1.5 factor, so that it can get the value is 9 kilonewton per meter intensity. So this is the load which is related to the ultimate load value. So after calculating this value of the loads, we have to calculate the moment of resistance as well as the bending moment for this particular slab section. So we know that the bending moment value for the simply supported section is WL square by 8. So we have to consider the load is 9 into 2.5 is the length of the slab divided by 8, so that it can get the value is 7.03 kilonewton per meter is the intensity of the load. Now we have to check for the moment of the resistance value. So we have the formula for calculating the moment of the resistance, which is equals to RU max into BD square. So basically for the grade of the M20 grade concrete with 415 grade steel provision standard system from the table 4.4.1. So M20 grade concrete 415 grade steel system. So the value of the RU is 2.76 here. So 2.76 we have to consider. Now we have to calculate the moment of resistance, which is equals to RU max into BD square. So we have to multiply this value 2.76 into 1000 into 90 square, so that it can get the values 24.8 kilonewton per meter intensity. Now we are calculated the bending moment value as well as the moment of resistance. So here we are calculated the value of the moment of resistance, which is of 24.8 kilonewton per meter, the intensity which is greater than the bending moment value, which is of 7.03 kilonewton per meter. So hence it is safe as per the moment of resistance value. So I will upload this PDF in the civil engineering Shravan application. You can download the PDF from the free PDF section. So I was already uploaded the cantilever slab design section PDF in the free PDF section of civil engineering Shravan application. So you can download the application for the reference. So now next step is to calculate the main steel. So we have the formula for calculating the main steel. AST equals to 0.5 into FC divided by Fy into 1 minus under root of 1 minus 4.6 into mu divided by FCK into BD square into BD. So if you substitute the value, then it will comes under the AST of 220 mm square value here. Okay. For now we have to calculate the percentage of the tungsten steel which is required for this slab section, which is approximately equal to 1000 into AST divided by 1000 D is the formula. So which is equals to 100 into 229 is the AST value we are calculated here, and 1000 is the factor, and D is the depth of the slab, which is of 90 mm we are considered here. So which is comes under 0.254 percentage for the slab section. So now here we are assumed that the PT assumed value is 0.3. So we are taken in the step number 1, which is related to the 0.3 PT value, and here we are getting the value of the percentage of the tension steel required is 0.254, okay, which is less than assumed value, hence it is safe. After this we have to calculate the area of the steel AST in order to determine the spacing between the bars for the respected 8 mm diameter bar. Okay, so let us consider 8 mm diameter bar. Just I am assuming pi by 4 into 8 square. This is the AST which is required, small AST for the slab section. Again, in the same process for calculating the spacing, we have the formula small AST divided by capital AST into 100,000, which is approximately equal to 50 divided by 229 into 100. So this 229 is the value here, and again this is the 50 value here. So which is comes under 218.34 mm value. So assume the value of the AST spacing is 200 mm for the bar section of 8 mm diameter bar as the main bar. So now we can see, as per the IS code provision standard system, maximum spacing value is 3D or 300 mm. So 3 into 90 is the depth of the slab, so which is approximately equals to 270 mm or 300 mm for this value. So the lesser value we have to consider. So here you can see the value of the calculated value is 200 mm spacing. So here 200 mm spacing is less than maximum value of 300 and 370 value. So we have to provide the value of the 8 mm diameter bar, which is placed at a distance of 200 center to center distance for this slab section. After this we have to calculate the area of the steel which is provided, which is equals to 1000 into A small AST divided by spacing. So 1000 into 50 divided by 200, which is comes under 250 mm square. So this is the reinforcement value calculation for the main steel bar. Now after this we have to calculate the distribution bar. Before that we have to check for the deflection for the main steel bar. So for the percentage of the tension steel required is 100 into AST divided by 1000 into D. So we are calculated the value of the AST, which is of 229. So 100 into 229 divided by 1000 into 90 here. If I consider the value, then it will be comes under 0.24 percentage approximately, which is 0.3 percentage maximum value assumed. Okay, so here it is not greater than, it is less than 0.3 assumed value, hence it is safe. But we have to check for the detailed checks for the respective reinforcement also. So here we have FS value is there, 0.58 into Fy into AST required by AST provided. So if I consider this AST required by AST provided, then it will be comes under 220.48 mm square is the value of the Fs. So percentage of the tensile steel provided, which is equals to percentage of the tension steel which is provided, which is equals to 100 into capital AST into AST provided divided by 1000 into D. So 100 into 250, this is the value which we are obtained from this particular calculation, 250 value here. So 250 divided by 1000 into 90, which is comes under 0.28 value. So here 0.28 value is less than 0.3, hence it is safe as per the check, as per the deflection point of view. But we have to check for the depth also for this slab section. Now we have to check for the minimum depth. So PT is 0.28 and FS is 240. So we have to consider this particular curve also, which is comes under this PT value. So we have to assume for the 0.28 value, we have to assume the modification factor MF value, which is comes under approximately 1.62. Now we have to check for the depth equals to span divided by multiplication factor into RB value, 2500 divided by 1.62 into 20, which is comes under 77. So here 77 value is less than 90 mm, which we are provided. So hence it is safe as per the consideration. So now the next step is to calculate the distribution steel. For the distribution steel, we have to assume the 0.15 percentage of the gross cross-sectional area as per the IS456-2000 code provision standard system, which is equals to 0.15 divided by 100 into 1000 into 110, which is of 165 mm square is the value of the AST which is required for the slab section. So by assuming 6 mm diameter bar, small AST equals to 28.3 mm square. So let us take 28 value, just I am assuming here. So spacing we have to calculate after calculating the diameter of the bar and AST value. So 1000 into small AST by capital AST into which is equals to 1000 into 28 divided by 165, which is comes under the value is 170 mm here. So, but as per the IS code, we have to consider the maximum spacing for the distribution bar also, which is of 5D or 450 mm, 5 into 80, which is approximately equal to 400. Sorry, not 5, 80, it is 90. 450 here. So here it is 450 value, again it is 450 value. So here we have to consider the whichever is the less value. So 170 value is less when you compare with 450 mm value. So we have to consider the distribution steel reinforcement, which is consisting of 6 mm diameter bar, which is placed at 180 center to center distance. Okay. So now we can see if you take the slab section for this particular panel which is of 2.5 meter and 3 meter panel, we have to provide the main bar, which is consisting of approximately 8 mm diameter bar, which are placed at a distance of 200 center to center distance. Again, distribution bar we have to provide, which is consisting of 6 mm diameter bar, which are placed at a distance of approximately 170 center to center distance. Okay. So this is the area of the reinforcement which is provided for the distribution bar. Now we have to check for the shear value. So this is also important. So design shear according to simply supported slab section, we have the formula WL by 2. So W is the load which we are calculated value is 9 into 2.5 divided by 2, which is comes under the value is 11.25. So now we have to consider the resistance, shear resistant value. So we have to calculate this shear resistance according to IS456 code provision standard system. We have the formula is multiplication factor into tau value into BD. Okay. So if you calculate the shear resistance, if it is getting higher value than the design shear, then it is safe as per the shear check. So from the table 4.4.2, we have to consider this K value, which is of 1.3 value. Okay. So if you consider this depth of the slab, overall depth of the slab is less than 150 mm. So that's why just I'm taking 1.3 factor here. So now for determining the tau u value, which is depends upon the mainly of percentage of the tension steel, which is given by the formula 100 into AST divided by BD. So now assuming the 50% of the bars are only used for the continuously supported sections. So we have to consider the AST value, which is having the formula which is of 1000 AST divided by S. So here we are taking the 50% of the bars only. That's why just I will divide this value with the 2. So 1000 into 50 divided by 200 divided by 2, which is comes under 125 mm square for the main bar reinforcement section. So now we will calculate the PT value, which is of 100 into AST divided by BD. If I calculate, then it is comes under 0.14%. From table 4.4.1 for the PT value of 0.14, and we have the tau u value, which is approximately equal to 0.28 value. So now we can see for the less than 100 AST by BD value 0.15% for the M20 grade concrete provision standard system, which is comes under 0.28. We have to consider. Now our next step is to calculate the VC value, which is equals to K into tau u into BD 1.3 into 0.28 into 1000 into 90, which is approximately equal to 32.76 value kilonewton per meter is the intensity of the shear reinforcement. So here we are assumed the resistance value we are calculated here, which is of 32.76 value, and design shear is 11.25. Hence it is safe as per the shear check point of view. So after that we have to check for the development length also. Development length is also important in the designing of the slab section. So basically for the development length for the M20 grade concrete provision standard system, which is of 415 grade steel provision system, for the HYSD bar, we have the development length LD equals to formula as 47.5, where 5 is the diameter of the bar which is used for the main bars. So as per the calculation, we are used the 8 mm diameter bar. So LD equals to 47 into 8, which is comes under this 376 mm. Okay. So now we have to calculate for the simply supported maximum LD value for the simply supported slab section, which is having 1.3 into M by V plus L0 value. So this is the bending moment value, this is the shear force value. So shear force value we are calculated WL by 2, which is approximately equal to 11.25 in this above step. Okay, so which is comes under this 11.25, and bending moment value we are calculated already, which is of 7.03 in the step number 3. Okay, so step number 3 I will show you that. This is the step number 3. The bending moment value we are calculated here, which is of 7.03 value. Okay, so again we have to calculate the value of the L0. So the L0 value is calculated by using a width of the slab beam section divided by 2 minus x1 thickness of the cover of the slab section plus 3 times x1 plus 3 times of phi. So for HOSD bar of 90 degrees bend section, this is the formula we have to consider as per the IS code. So which is equals to 230 mm divided by 2 minus 25 mm is the value x1 plus 3 into 5. So which is of 8 mm diameter bar, which is approximately equal to 114 mm. Now we have to calculate maximum LD value 1.3 into 7.03 divided by 11.25 plus 1.114, which is approximately comes under 520 mm. So here calculated LD value, maximum LD value is 520. So which is greater than the LD value which is we are obtained from this particular calculation development length, which is of 376 mm value here. Okay. So hence it is safe as per the development length also. So we have to provide the main bar which is consisting of the 8 mm diameter bar which are placed at 200 center to center distance for this particular slab section. Again in the same process we have to place the distribution reinforcement bar which is having 6 mm diameter bar which are placed at a distance of 170 center to center distance for this particular slab section. So this is the complete calculation part which is related to simply supported slab design as per IS456-2000 code. So I will upload this PDF in the civil engineering Shravan application. You can download the PDF and you can check the complete details about the complete step-by-step calculation part which is related to the cantilever slab section design according to IS456-2000 code provision standard system. So the complete concepts related to the STAT Pro, ETAP, SAP 2000 and etc. courses are available in civil engineering Shravan application. So you can download the application. The download link is direct link is available in the below description of this video. So thank you for watching this video. See you in the next one.